Welcome to class. So far, we have got an idea that solutions might not be out there. And then we learn some vocab so that we can get some hope. Actually, maybe there are solutions out there sometimes. And now we need to pause again for a little more vocabulary before we can get to the bread and butter of this conversation. So, let's get started. Now we say functions are linearly independent if I have, let's say, n of them, and n non-zero constants. Those are the c's up here. If I take c1f1 plus c2f2 plus so on and so forth, add them all up in this way, if that is non-zero, regardless of which set of constants I chose, then we say the set of functions is linearly independent. And we borrow this language from the fact that this left-hand side here, we would call a linear combination of f1 through fn. By the way, we usually talk about this in the context of an interval. Because I get a function of x over here, it's usually better to specify what interval we're looking on. Now I have a couple of quick examples, because this definition is maybe a little funky here. Up first, I actually have the harder thing to do, which is to show that things are linearly independent. But here's a simple case. If I have the function 1, x, and x squared, and I add them all up in a linear combination, right? That means I take c1 times f1 plus c2 times f2 plus c3 times f3. I get a quadratic equation. And we actually know the solution to this guy from the quadratic formula, right? It's negative b plus or minus the square root of b squared minus 4ac all over 2a. And that looks confusing at first, but remember, while this square root term might end up being 0, depending on how we choose c1, c2, and c3, the constants themselves aren't allowed to be 0. That said, I've always got a non-zero over a non-zero, right? That is non-zero. It's a little easier, though, to show when functions aren't linearly independent, like in this case. If I add up a combination of them, really to show they're not linearly independent, I just need to find a single way to add them up to be 0. The magic numbers are to take negative 4, or I suppose c1 to be 1, c2 to be negative 4, and c3 to be 3. And then you'll notice c1 times f1 plus c2 times g's, plus c3 times g3 is 0. And it turns out that this set of functions is linearly independent regardless of my interval. This set of functions is linearly dependent regardless of my interval. Now, it turns out there's a more straightforward way of determining whether functions are linearly independent or not, assuming they're sufficiently differentiable. But that method is going to involve this guy, the Wronskian of a set of functions. The Wronskian is the determinant, notice my vertical bars here, implying I take the determinant of all of the functions across the first row, and then I take their derivatives down until I complete a square matrix. So I have all of the functions across the top, first derivatives, second derivatives, so on and so forth. Of course, if you count, I have n functions, then I need n rows, so I get down to the n minus 1th derivative. But this notation looks a little bit confusing, and by the way, it involves taking a determinant. If your linear algebra is a little bit rusty, or if you don't recall how to take a determinant, I have linked a really good video on that in the description of this video, so go check that one out if you need a quick refresher on how to take determinants of matrices. Otherwise, let's do an example. We just saw this set of functions previously, 1, x, and x squared. Let's compute their Wronskian together. The Wronskian is the determinant of, since I have 3 functions, a 3 by 3 matrix. I put my functions across the top row. So 1, x, x squared. And then I take derivatives going down each row until I've completed the square. Notice I need more rows, so I take the derivatives. Derivative of 1 is 0, Derivative of x is 1. Derivative of x squared is 2x. I still don't have all three rows, so I go again. Derivative of 0 is 0. Derivative of 1 is 0. Derivative of 2x is 2. Now, I take the determinant. I can simplify this guy to just being the 2 by 2, 1, 2x, 0, 2. Again, check that video link in the description if you need a little refresher on how that works. Last but not least, I get 2 as the Wronskian of these functions. Now, generally, we may have a function of x, not just a constant. Let's look at an example of that. Let's try the other set that we saw earlier, shall we? Let's compute the Wronskian of 4x minus 3x squared, x, and x squared. The only thing this changes about my initial setup is that the first function has changed. I have three functions still, so I'm still going to set up a 3 by 3 determinant. First function, second function, third function. And I'm going to take derivatives down the rows. So derivative here is 4 minus 6x, 1, 2x. Take derivatives again, negative 6, 0, 2. Think it's easiest to use that middle column here for our determinants. So we will get negative x times the 2 by 2, 4 minus 6x, 2x, negative 6, 2, plus 1 times the 2 by 2, 4x minus 3x squared, x squared, negative 6, and 2. After cleaning it up a bit, I just get negative 16x. See? Function of x. But how is this related to linear independence? Well, it turns out that relationship is pretty deep, actually. Functions are linearly independent if and only if the Wronskian is non-zero on that interval. Of course, we can really only use this theorem when our functions are sufficiently smooth, or I can differentiate them enough times to build the Wronskian, but in the examples we've seen so far, that's been the case. Remember, we got the Wronskian of 1x and x squared is 2? That, in and of itself, is enough to show that they're linearly independent, because, and this is true, 2 is not equal to 0 ever, right? Ever. So this means that 1x and x squared are linearly independent on any interval. In fact, on all real numbers. Now, we're not so lucky for this set of functions that we just saw the Wronskian of 4x minus 3x squared. X and x squared is negative 16x. Do you notice that this can be 0 when x is 0? But outside of that, we're actually in the clear. So these are linearly independent still on any interval that doesn't contain 0. While this might not be as elegant as showing, hey, look, this linear combination is non-zero regardless of which values I pick, it's a lot more straightforward to just compute the Wronskian and check. And again, this may not be as elegant as finding a really cool counterexample where you can linearly combine these functions to add up to 0, but this is still a brute force way to do it that's maybe a little safer.